This is part 13 of the series Applications of Differentiation. In this part we have another function that we're going to sketch, and it's a rational function, and I'm going to start off with the zeros of the function. The zeros of the function can be found at the zeros of the numerator, and if you look at this numerator you'll see that it doesn't factor. So let's go to the quadratic formula and see if it actually has any real zeros. So we have negative b plus or minus the square root of b squared minus 4 times a times c. And you can see that this discriminant is going to be 4 minus 16, which is a non-real number, so this function has no zeros. So it has no x-intercepts. For the y-intercepts, we'll just set the x to 0. And this, and this go to 0. And we have 4 over negative 2, which is just negative 2. So the y-intercept is 0, negative 2. So now let's look at the asymptotes of this function. You can see that this function will have a vertical asymptote at x equals 2 because this denominator is 0 at a positive 2. So it has a vertical asymptote at x equals 2. And for the horizontal asymptote, what we're going to do is we're going to take the limit as x approaches infinity. So limit as x approaches infinity of this function, we're going to have to divide the numerator and denominator by x squared to eliminate the problem of an indeterminate form. If we evaluate this by direct substitution, the numerator and denominator both go to infinity, and that's not good. So x squared divided by x squared minus 2x over x squared plus 4 over x squared, and x over x squared minus 2 over x squared. This gives us 1 minus 2 over x plus 4 over x squared all over 1 over x minus 2 over x squared. When we take this limit as x approaches infinity, these terms all go to 0. This one goes to 0 and this one goes to 0. So we can see that this function has no horizontal asymptotes because it increases without bound as x approaches infinity. So this function has no horizontal asymptotes. But now because this function does increase without bound, there's a possibility that there may be a slant asymptote. And if we notice that the degree of the numerator is 1 greater than the degree of the denominator, we can see that there's a great likelihood that there is. So what we're going to do is we're going to do some synthetic division here to find out what that slant asymptote is. So what we have then is x is 2, and that's going to go into, put the coefficients of our numerator in here, drop down the 1, 2 times 1 is 2, and that's 0. So as we can see, we're not interested in the remainder. When you divide x minus 2 into x squared minus 2x plus 4, we get y equals x. And y equals x is our slant asymptote. All right. So now that we have our asymptotes, we're going to go ahead and look for our extrema. In order to do that, we're going to have to take the first derivative of this function. So let's give ourselves a little space and we're going to do f prime of x. And we're going to use the quotient rule. So we have low d high, low, times the derivative of the high is 2x minus 2 minus high, x squared minus 2x plus 4 d low. Derivative of the low function, the denominator, is just 1 all over low squared. Now we'll simplify that numerator. So let's give ourselves a little more room. And we'll multiply this through. And we have 2x squared minus 2x minus 4x plus 4 minus x squared plus 2x minus 4 all over x minus 2 squared. Simplifying it again, we have 2x squared minus x squared is an x squared. 2x, negative 2x plus 2x, they go away. We have a 4x left, so minus 4x. And this positive 4 and negative 4 cancel each other out. So that whole thing over x minus 2 squared, which gives us our f prime of x. So now we're going to look for our critical numbers. Critical numbers occur where the function is either 0 or undefined, and we can see that the numerator is 0. If we factor out an x, we have x minus 4. So we have x equals 0 and 4 as two of our critical numbers. Now our other critical numbers will occur where the first derivative is undefined. That occurs at x equals 2, but notice that we have a vertical asymptote at x equals 2, so 2 is not a critical number. Our only critical numbers are 0 and 4. So let's go ahead and put that in here. All right. Now let's go ahead and take our second derivative. So we're going to be using the quotient rule, so we'll need a little space. So I'll start it over here, and f double prime of x equals low x minus 2 squared d high 2x minus 4 minus high x squared minus 4x d low, and this is going to be chain rule, times the derivative of the inside is just 1. So we have low d high minus high d low all over low squared. Now let's go ahead and simplify this numerator. If you notice, there's an x minus 2, x minus 2, and an x minus 2. So every one of these terms has an x minus 2 in it. So let's go ahead and get those out. So one of those x minus 2's go away. We have x minus 2 times 2x minus 4 minus, this guy goes away, so we have 2 times x squared, and negative 2 times negative 4x, which is plus 8x. So I just kind of combined a step there. All over x minus 2, and one of those x minus 2's went away, so that's x minus 2 to the third. All right, let's continue to simplify this. Let's multiply this numerator out. So x times 2x is 2x squared. x times negative 4, negative 4x, minus 4x plus 8 minus 2x squared plus 8x all over x minus 2 to the third. So here we have negative 4x and negative 4x is a negative 8x, which cancels out with this 8x. This negative 2x squared and this 2x squared cancel out. So all we're left with is the 8 in the numerator. So what we have is, let's put it over here. We'll put it over here. F double prime of x is 8 over x minus 2 to the third. Ordinarily, I would have stopped at the first derivative and done my first derivative test. I just kind of got caught up in the derivative moment there. But let's go back to this first derivative and let's use these critical numbers to find our extrema. So we'll put a line across here. Our critical numbers are 0 and 4. Our test values will be negative 1, 1, and 5. So evaluating our first derivative at negative 1, this is positive. At 1, it's negative, and at 5, it's positive again. So we can see that at 0, we have a max. So this is a maximum. And at 4, we have a minimum. And the maximum is going to be 0, negative 2. The minimum is going to be 4, 6. So let's go put those up here. So we have a max at 0, negative 2, and a min at 4, 6. Now let's take a look at concavity. So down here we have our second derivative, and our possible points of inflection are going to occur where the function is 0 or undefined. Here the function doesn't have any zeros because the 0 of the numerator is a constant. It doesn't cross the x-axis. And the denominator is 0 at x equals 2, but again, remember that the function has a vertical asymptote at x equals 2, so this function has no points of inflection. So we can say points of inflection, none. But we can still determine concavity, and we're going to use this point as our anchor point to determine what the function's concavity is to the left and the right of that asymptote. So let's go ahead and draw a line here. Our asymptote will be here at 2, and so we're going to evaluate the second derivative at 0 and 3 to see what the concavity is on those intervals. And so when we evaluate our second derivative at 0, we see that it's negative, so we're concave down from negative infinity to 2, and at 3 it's positive, so we're concave up from 2 to infinity. So now let's go ahead and plug in all our information into our graph and see what it looks like. And so we see we have no x-intercepts. The graph does not touch the x-axis. Y-intercept is at 0, negative 2. We have a maximum at 0, negative 2, and a minimum at 4, 6. We have a vertical asymptote, x equals 2, and a slant asymptote at y equals x. Now, to plot this function, we can see that the function has to exist down here, and so it can't exist up here because of the asymptote and the fact that the point is existing down here. So we know that the function has to go here, especially because it's concave down in this region. And if it was up here, it would have to be concave up. So there's our first lobe. Second one, we see we have a minimum point here. The function is concave up from 2 on. And here we have our second lobe. Now let's work another problem.